In this video, I am going to walk us through a proof of Heron's formula, which is also known as the semi-perimeter formula for the area of a triangle. Just as a reference point, remember, if you have a triangle and you know three sides, A, B, and C, if you let S equal 1/2 times A plus B plus C, which is also known as the semi-perimeter, then the area of the triangle is the square root of S times S minus A, S minus B, S minus C. That right there is what we would like to prove. And it's going to take a little bit of work to get there, but we're going to basically build several pieces and then put them all together in one big jigsaw puzzle, and it's going to work, okay? So follow me along here. Consider that the area of a triangle, which we often denote as the letter K, is easily derived to be 1/2 times AB times the sine of the angle between them. Right? That's something that we know and quickly derive from letting H be that height and the base be B if this was angle C over here, and this is angle A up here. We know that the area of the triangle is 1/2 base times height, and the H turns out to be A sine of C, just from the definition of the trig functions in terms of right triangles. So we get this formula. We know that to be true. Now let's start building some pieces that we're going to need to put together. And again, it's going to seem kind of disjointed and like a jigsaw puzzle, but once all the pieces are in place, you're going to see that the Heron's formula falls right out. So recall that sine of 2 theta has a trigonometric identity. We know that is always equal to 2 sine of theta cosine of theta. So if we consider that sine of C, namely this sine of C up here, could be thought of as sine of twice an angle called C over 2. If we let this right here be our theta, then we can rewrite this as 2 sine of C over 2 cosine of C over 2. Which would mean then that my area, which we know to be true, 1/2 AB sine of C, could be written as 1/2 AB times, and now replacing this right here in for this right here, gives us 2 sine of C over 2 cosine of C over 2, and the 2 and the 1/2 cancel, so we're left with AB sine of C over 2 cosine of C over 2. So I'm going to label this as equation 1 because we're going to come back and refer to this later on. Basically what I'm going to do is I'm going to look at these two pieces here, and I'll highlight them in green and blue. I want to look at, first I'm going to look at cosine of C over 2, and then I'm going to look at sine of C over 2, each separately, and plug in some results from a little bit of fancy footwork, as it were. So let's consider, and I'm going to go ahead and start with the second one. Let's consider cosine of C over 2. Recall from our trigonometric identities that cosine of a theta over 2 is always plus or minus, depending on what angle theta over 2 ends up in, 1 plus cosine of theta all divided by 2, which would then mean that cosine squared of theta over 2, by simply squaring both sides, is 1 plus cosine of theta all divided by 2. So in other words, since we're looking at cosine of C over 2, we can simply rewrite it based on what I just said. We know that cosine squared of C over 2 is 1 plus cosine of C all divided by 2. Now also recall the law of cosines that involve cosine of c. You'll recall that c squared is equal to a squared plus b squared minus 2ab cosine of capital C. So here's what I want to do. I am going to take, and I'll use red here to just move things around. I want to move this c squared to this side, and I want to move this whole term here to the left-hand side. And in doing so, I would end up with the following. I have that 2ac cosine of capital C is equal to, not AC. Why did I write AC? All right, let's fix this. AB. AB. So fix that from my law of cosines. I wrote that incorrectly. We have a squared plus b squared minus 2ab cosine of c. I want to move 2ab cosine of c to the left-hand side and subtract c squared to the right-hand side. And divide both sides now by 2ab, which would give me that cosine of c, okay, for any angle C in a triangle would be equal to a squared plus b squared minus c squared, all divided by 2ab. Okay? So now, if I take this, which let's say we call it, we'll call this up here equation 2. I want to take this and plug it into equation 2. In other words, I want to stick it right there where that cosine of C is. Okay, so in doing so, what I end up with would be that by 2, we know cosine squared of C over 2 is equal to 1 plus this fraction here, which is a squared plus b squared minus c squared over 2ab, all divided by 2. Again, all I've done is taken this expression here and stuck it in for right here, right there. And now a little bit of algebra. Can help simplify this. First of all, what I would like to do is get rid of the complex fraction here. So I'm going to multiply everything on top and bottom by 2ab. That gets rid of the fraction inside the fraction. So I end up with 2ab plus a squared plus b squared minus c squared, all divided by 4ab. And if I rearrange that a little bit, I get a squared plus b squared, actually a squared plus 2ab plus b squared minus c squared, all divided by 4ab. All I did was rearrange the numerator. And what jumps out at me is the fact that this first part right here, which I'll highlight in purple, happens to be a perfect square trinomial. So this is actually a plus b quantity squared minus c squared, all divided by 4ab. And in fact, since this is now something squared minus something squared, I can rewrite this on top as a difference of squares, which means it factors. This is now equal to a plus b minus c times a plus b plus c, right? This is like something squared minus something squared, which means it's the something minus the something times the something plus the something, all over 4ab. Now, I'm doing a lot of different steps that kind of seem to come out of nowhere. What I don't want you to be able to do is know why I'm doing the next step. What I would like you to understand is that it is in fact true. Right? That's all you have to agree upon, is that each step that I take along this process is something you understand why it's true, not why I'm doing it necessarily, because you'll see it fits all together at the very end. I had a professor whenever I was in in my undergraduate work at Wayland that used to say that a lot of these proofs are like just taking a whole bunch of wood and nails and screws and throwing it up in the air, and then when it falls down to the ground, it's a doghouse. So imagine that I'm now taking all the pieces and throwing them up in the air. Just verify that they're coming together in a way that makes sense. That is, you understand why it is true what it's true. For example, you understand up here whenever I took this 2AB on top and bottom, by multiplying by the same thing on top and bottom, I do not change the value of the fraction, but I do simplify it so that I no longer have a fraction inside of a fraction. And all I did was distribute this across each term, and the same thing on bottom to get what I ended up with. That I can easily rearrange terms as I move to the next equal sign, and that I can then factor that perfect square trinomial. Now here's the key. Notice that if S is 1/2 A plus B plus C, then 2S is A plus B plus C. That is, right here, I have a 2S. Right from right there. Also, 2S minus 2C would be A plus B plus C minus 2C, which is A plus B minus C. So this right here, and maybe I should write this in a different color so you can see it stand out here. I'll do this in red. This right here was 2S. This right here is 2, and just factor the 2 out, that's S minus C. 2 times S minus C. Put all those pieces together, and what do you have? You have that the cosine squared of C over 2 is 2 times S minus C times a 2S all over 4AB, which the 2's multiplied together to give you 4, cancels with the 4 on bottom. You have S times S minus C all over AB. Now if you take the square root of both sides, you have cosine of C over 2 equals S times S minus C over AB with the square root around it. And technically you have to remember that there would be a plus or minus out front, but it actually has to be plus because angle C is always between 180 and 0. That is, it's some angle between 180 and 0 and 180 degrees. If you take half of that, it's going to be between 0 and 90, and the cosine and sine of anything between 0 and 90 is positive. So we know that's going to be positive because of that reason right there. So cosine of C over 2 is the square root of S times S minus C over AB. This was what's going to go in the green area up above. Right, way up here. In this Formula 1, we're going to be able to replace that cosine of C over 2 with that radical right there. Now, moving forward. As our next step, we're going to now consider, similarly, what happens if I look at sine of C over 2. Sine of capital C over 2, which would be plus or minus the square root of 1 minus cosine of C divided by 2. There's a minus sign instead of a plus sign in there. So following the same rationale, we can say sine squared of C over 2 is 1 minus cosine of C all divided by 2. Now apply a similar approach that we did above here. We'll call this equation 3. Cosine of C is A squared plus B squared minus C squared over 2AB. Sine, well, we'll just call it 3. namely that cosine of c, we have a squared plus b squared minus c squared, all divided by 2ab for any given triangle, all divided by 2. And using the same approach as before, if I multiply the top of this fraction by 2ab and the bottom by 2ab, I get 2ab minus a squared plus b squared minus c squared divided by 4ab. Okay, so on top this becomes 2ab minus a squared minus b squared plus c squared over 4ab, or c squared minus, and I'm going to just put the c squared out front because then this second term becomes the perfect squared trinomial, a squared plus 2ab minus b squared over 4ab. Or if we factor out the minus, that becomes c squared minus a squared minus 2ab plus b squared over 4ab. So all I did here was rearrange. All I did here was pull out a minus sign. And now if I factor that second term in the numerator, I get a minus b quantity squared over 4ab. So this then means that I can rewrite sine squared of c over 2 as c plus an a minus b times a c minus an a minus b, if there's a difference of squares on top. Something squared minus something squared means something plus something times something minus something. And just simplifying inside, that gives me, this first one becomes a c plus a minus b, and the second one is a c minus a plus b, just distributing the minus sign, over 4ab. So what I really want to take a look at here is these two things, this guy here and this guy here. It turns out those are going to be something in terms of s and c, or s and a, s and b. Again, recall 2s was a plus b plus c. So if I do 2s minus 2b, that's a plus b plus c minus 2b, or a plus c minus b, which is also c plus a minus b, this term right here. Similarly, if I do 2s minus 2a, I would get a plus b plus c minus 2a, which is a b plus a c minus an a, or a positive c minus an a plus a b. That's this term right here. So the key is this piece here and this piece here are in that numerator. So sine squared of c over 2 is, and let's factor out the 2 in both cases, 2 times s minus b and 2 times s minus a. I get a 2 times s minus b on top here times a 2 times s minus c from here, all over 4ab. And then the 2's will cancel with the 4, and I'm left with s minus b times s minus c all over ab, which then means that sine of c over 2, by simply taking the square root of both sides, is s minus b, s minus c all over ab. Some algebra wizardry, but now we've got back to something that I can plug in for, and I'll highlight this, whatever color I did it up here. That's going to be the blue part from Formula 1. So this here, I can plug into my Formula 1. Okay, so I've got it, what all pieces that I need now for finishing this proof. So let me go grab my blue pen, and we say from 1. The area was 1/2. Actually, it wasn't even 1/2. The 1/2 was gone. It was AB sine of C over 2 cosine of C over 2. So plugging in what I've got, sine of C over 2 from the blue up here is the square root of S minus B times S minus C divided by AB. And then from above, in green, cosine of C over 2 is S times S minus C over AB, all in the radical. S times S minus C all over AB. So I can combine those together. A, B, square root of 1 big radical is going to be S minus B, S minus C times S. Wait, I messed up somewhere. Where's this should be A here. Got to fix that. I apologize. All right. A good lecturer online would go back and fix that whole video, but I don't want to re-record it all. So from page 109 in your notes, go back and change this C to an A. So it turned out to be S minus B times S minus A over AB inside the radical. So I have an A here, an A here. And notice all the pieces are there for Heron's formula. We're almost to Heron's formula. Because we got S minus B, S minus A times S minus C. You got S, S minus A, S minus B, S minus C. But we got this AB, which is now A squared, B squared. You can pull in this AB that's sitting out front inside the radical by just saying, you know, this is square root of A squared, B squared. Since A and B are positive quantities. And then write that as one big radical. So times S minus B, S minus A, S and S minus C all over A squared, B squared, which will cancel out and leave you with, and simply rearranging the factors, S times S minus A, S minus B, S minus C. Heron's formula is proved.